In this example, we're going to take a look at enthalpy calculations, and we're specifically looking at how specific properties are related to flow rates in this problem. So you'll see I've made a lot of little notes related to this problem. So let's just walk through what we've got. We've got a specific internal energy of helium, which is at a specific temperature and a pressure. So remember, specific internal energy, I'm going to draw it over here. That's going to be a U with a little hat on it. Okay, and that's got units of 3,800 joules per mole. The units are also an indication that it's a specific internal energy. We have a specific molar volume, so that's going to be a V hat. And the fact that it's molar tells us that it's related to N or to N dot. So that's important here. And that's at the same pressure and temperature as the specific internal energy, and there's the value for that. So we've got liters per mole. That gives you the indication that it's a specific property. We want to know the specific enthalpy of helium at this temperature and pressure, and that's going to be an H with a hat on it. But then we also want to know the rate at which enthalpy is transported by a stream. And that stream is flowing at a molar flow rate. So we know that there's an H dot that we want to find as well, and an N dot that we want to find as well. And the other piece of information that I will give you is a unit conversion. So I would give this to you on an exam. I do not expect you to know this or know how to look this up. This is a specific, basically, unit conversion that would help us basically solve this problem. So we'll see this later on. So basically, when we're going through this problem, we know that enthalpy itself, the specific enthalpy, is defined as, remember, 3 equal sign means is defined as, the internal energy, the specific internal energy, plus the pressure times the specific internal volume. So, or excuse me, specific volume in the system. So if we want to find H hat, right, the overall strategy is going to be we want to find this H hat because we're really looking for this guy right here. And we know there's a relationship between this number, the H with the hat, the H dot, and the N dot in this system. Okay, so we've got to find this H hat first. So that's our first step. So the first thing that we want to do is we want to make sure that U hat, V hat, and P are all in correct units, and we want to make sure that we pull those numbers correctly out of the problem. So we can pull U right out of the problem. It's 3,800 joules per mole, so that means that we have a U per N, right? This is specific internal energy. V hat can also be pulled specifically from the problem. We can have 24.63 liters per mole, so that's a V per an N. And then if we look at pressure, we have 1 atm of pressure, but we're going to need different units of pressure basically to be able to solve this problem. I apologize, it was a bit sideways. There we go. We're going to take that unit conversion that we have up above and multiply it by this 1 atm to get 101.3 joules per liter. And when we start to solve for this H hat, you're going to see why these units matter. So let's come down and find our H hat. So let's plug in our numbers. Here's the specific internal energy, here's that pressure, and here's that specific volume. Now, if you look closely, remember dimensional homogeneity? Joules per liter times liters per mole is going to give us joules per mole. And we can add joules per mole to joules per mole. So that's kind of why we needed to do this pressure rearranging so that we had that dimensional homogeneity as we moved forward. Then if we do that calculation, we're going to get that the specific enthalpy is 6,295 joules per mole. Now, remember, the ultimate goal is to find H dot. So we know that your specific property is defined as that property divided by either moles or mass. And in this case, we're dealing with molar rates. So everything can have a dot on it or everything cannot have a dot on it, and it's still the same over here. So therefore, we can rearrange this equation and we can say if we want to find H dot, it's going to be the molar flow rate times the specific molar enthalpy in the system. And that is the specific molar enthalpy. So maybe it would be good to write that down. It's not just the specific enthalpy, it's the specific molar enthalpy. Hard word to say. Because it's related to moles in the system. That's important. So let's take our numbers. Let's take our 250 kilomoles per hour that's given in the problem. Let's take that number we just found for specific molar enthalpy. Let's make sure that we have either moles or kilomoles, not both. So let's make sure that we translate by using this unit conversion. And then we find that the enthalpy flow in the system is 1.57 times 10 to the ninth joules per hour. So not, again, a terribly hard example, just like our example 7.2 where we looked at the piston, but really trying to get you to understand how your specific properties are related to your flow rates. That's the key thing out of this problem. So if you understand these relationships, you're in a good place. The other key thing about this one is the fact that everything is related to molar quantities. So watching our units and making sure we're all in molar quantities is going to be an important thing for this particular problem. Remember that this could also be written in terms of mass. So if we could also write this in terms of mass, we'd really have to watch our units down here as well.